What is up, 7th grade? This is lesson 7. Our objective for today is to demonstrate your ability to name lines, angles, and planes and work with those things in amongst and around them. So first of all, let's just see about going through defining. We're going to go through a bunch of defining and helping us understand. Then we're going to go through some examples and some application of this. So first of all, a space, and that's what we live in. We live in a three-dimensional world. That's why I put 3D here. That has height, depth, and width to it. And so space is just that, like our world and outer space extends forever in all directions, at least all directions that us as humans can imagine and think about, because we live in a three-dimensional world. Now a plane is only two-dimensional. A plane is like a flat surface. Maybe think about like your floor. It extends forever in all directions, but it's just flat and it has no thickness to it. So it's a two-dimensional. It has just like a height and a width to it, but has no depth. It's just paper thin, even thinner than paper. A line is just a one-dimensional. I guess maybe I can, like a plane, normally we draw like this. Even though a plane doesn't have any edges, that's how we draw a plane. And a line just extends forever in two opposite directions and doesn't ever stop. And then a point is just a dot. Okay, it has no height, width, or depth. It's just a specific location, like a pinprick. And that's why it says it's a zero dimension, right? This is 1, this is 2, this is 3. This one has 0 dimension. Okay? Now moving on from there, a piece of a line, like if I were to take a line and then cut it, so it starts at a point and goes off in one direction, we call that a ray. And I guess, so a ray we name by its starting point and a point that it passes through. So maybe this starts at P, and this point is Q. So PQ, so we name this PQ, and we put like a little line above it pointing off to the right. But we always start with its starting point, where it starts at. Even if the ray was going like this direction, and this point was T and this point was S, we'd name it TS. Like that. Okay. Now a line we name by just simply 2 points on the line. Maybe I'll use a different color. Maybe this is A, B. So if we wanted to name that line, we'd say AB, and you put a line with arrows above it. Now, since AB would also be the same thing as BA. Okay, so that's kind of either directional. And then points we just name by, like, that's point A. And then a plane we would have to name with 3 points on there, like we'd say plane ABC. Name with 3 points. Now a segment is just simply a piece of a line. So it has a starting point and it has an ending point. So I'll call this LM. So this would just be LM, and we put a little line over it without the arrows. So that's line segment, LM. Now, down here, I want to talk about the segment addition postulate. That sounds big words, maybe scary, but all it simply means is that if you have a segment, this piece plus this piece, if you add two pieces of it together, will give you this whole piece, the whole thing. So one piece plus the next piece equals the whole thing. Alright, when we're talking about lines, if they cross each other, then they're what we call intersecting lines. They're intersecting lines. If they never cross each other, like this one here, then we call those parallel lines, and this is a short abbreviation for parallel lines. So these are parallel. And if they intersect at a particular angle, like at a corner at 90 degrees, we call that perpendicular lines, and we use this symbol for perpendicular. Now, if they intersect and they're not at a right angle, like this example up here at the top, okay, when they intersect but this angle in here is not 90 degrees, then this is what we call oblique lines. We call them oblique lines. So if they intersect but not at a right angle, we call them oblique. Okay, let me come on down to the bottom of this page. We're talking about skew lines. Skew lines are not in the same plane, which means that they're not on the same surface. So maybe think about a golf course being a plane, and then the golf tee would be another line that kind of crosses through it. So they're not in the same flat surface. So think about this right here being a box, right? So one of them, this one, and this one do not ever touch each other. However, they're not parallel, because parallel would be in the same plane. So they don't touch each other, and if they're not in the same plane, then we call them skew lines. Now moving on to angles, if we're going to talk about angles, this is when we have two rays. So look at, there's a ray AB and a ray AC, and they share the same starting point, in this case A. We call that an angle. Okay, that starting point of both the rays we call the vertex, and those two rays we call the sides of the angle. Now there's four basic types of angles. The first one is acute angles, because oh, they're just so tight and tiny and cute. Those are between 0 and 90 degrees. So think about a 0 degree angle would just simply look like this, right? Like a ray, there's 0 degrees between them. A 90 degree angle would look like this, which I guess maybe I should have written down here. Put a little box in the corner to illustrate that 90 degrees. So that means an acute angle would be something between those two, maybe something like this, like a 30 degree angle. That's just an estimate of what a 30 degree angle looks like. Now 180 degree angle, if you were to turn around 180 degrees, you're facing the exact opposite direction, this just forms a line. That's why we call it a straight angle. Okay? And then, so between 90 and between 180 is something we call obtuse. For some reason, I think of the word obtuse and I associate with the word obese, like big or large. So I think of those as big angles. So acute angles are real small, and obtuse angles are large. So we can classify angles by one of those things there. All right, so let's go ahead and get started on some of these, and this is from the practice set. Part A says, name a point on this figure. So I'm noticing, first of all, that I have 1, 2, 3, 4 points. So I have to name one of those points that is not, I'm going to go ahead and highlight that word, that is not on ray BC. So let's think about ray BC for a second. BC is going to start at B and go through C. Now remember, it goes on for forever, and that direction just means it's going to keep going and going and going and going all the way out through D as well. So since I'm looking for a point that's not on there, I'm going to say point A. Point A. Part B. In this figure, XZ is 10 centimeters. So from here to here is 10 centimeters. And it says, and YZ from here to here is 6 centimeters. Find XY. Notice there's no line or anything above it, which means we're wanting the length from X to Y. The length from X to Y is what we're looking for. Well, I know if this whole length is 10 and this length is 6, all I need to do is I need to say that 10, subtract the 6, and I will get 4. So this length over here is actually going to be 4 centimeters. So I don't need that question mark anymore. So that's what I'm putting for my answer, 4 centimeters. Okay, part C says draw two parallel lines. Remember, parallel lines are lines that never intersect. That kind of, if I get confused, the two L's in parallel help remind me because they're right next to each other. Parallel, those lines are parallel, because perpendicular, the next one, are ones that do intersect, and particularly at a right angle. Two lines intersect would look like this. These are perpendicular lines. Okay? And then part E says, draw two lines that intersect but are not perpendicular. So that's probably even easier. Two lines that cross but are not perpendicular. And then it says, what word describes the relationship of these lines? And if you remember right, if you remember we talked about this, we call these oblique lines. We call them oblique lines. All right. Going on to F, it says draw a right angle. So again, this one's going to have like a corner of a paper. And it says draw an acute angle. Draw an obtuse angle. Two intersecting segments, this is I now. Two intersecting segments are drawn on the board. One segment is vertical and the other is horizontal. Are the segments parallel or perpendicular? So let's draw that real quick. If there's two segments, here's a vertical one, at least approximately vertical, and here's a horizontal one, at least kind of horizontal. Remember, parallel, like those L's in there, never cross each other. They're like train tracks or something. So in this case, this would be perpendicular. So I'd say perpendicular. All right. J says describe a physical example of parallel lines. Parallel lines. Well, I think I just said one. Maybe train tracks. Train tracks are an example of parallel lines because each side of those never cross each other. Describe a physical example of intersecting planes. So two flat surfaces that intersect each other. Oh, I think of one here. What about a wall and the floor? Because the wall is like a plane and the floor is like a plane. So that would be an example of two of them intersecting right there at the corner in your room. Lines intersect at a point. So that's an information. So two lines, when they intersect at a single point. Right? It's the only thing they have in common. But it says planes intersect at a blank. Well, think about what we just talked about, the wall and the floor where they touch. There is a line at the corner that goes all the way through. That line, kind of where the floor and the wall touch, is both on the wall and on the floor. So the answer to this question is a line. The answer to this question is a line, or the blank. So lines intersect at a point, planes intersect at a line. Your homework is starts on page 51. You can do all of them from lesson 7 and all of them from lesson 6, and then 10 more of your choice.